All right, good afternoon. So let me start by choosing violence against my lame colleagues here. So let me start by saying that nothing that my colleagues here will present could have been done without computers. Nothing. And if we look under the hood, what is inside of the computer, you will see those integrated circuits. And that's why I'm getting 1 extra minute, because the slide was not there. And you see on the top right corner, left corner, you see a die of an Apple A14 chip that it has a transistor side of 5 nanometers, and it has 11.8 billion transistors. That's an amazing amount of transistors. We entered the era of the multi-billion transistors integrated circuits. Now, what is the problem with that? Is that if you look at the next slide, you'll see that that we are reaching the computational power of all these integrated circuits are reaching basically the world's energy production if we continue this way. So the solution that has been proposed in computer architecture is to optimize the computer architecture of the integrated circuit to domain-specific applications. And that's what happened from the A8 processor that you see here from Apple, where you have multiple CPUs, multiple GPUs, and many different hardware accelerators. These are dedicated hardware modules that you can do specific tasks much more energy efficiency than your CPUs or your GPUs. So what we have been doing in the lab is building design methodologies that allow to create these complicated heterogeneous integrated circuits much easier than what was done before. So think about it. In the past, in the 80s, in 70s and 80s, the way to build these integrated circuits was for stitching gates together and connecting them. Can you believe building 2 billion, 11 billion chip transistors by stitching individual transistors together is not very scalable, isn't it? So what was proposed in the 90s and 2000 and what companies are doing now is they're using low-level hardware description languages. You might have heard about Verilog and VHDL. But the very low level, you see here an example of how to build an 8-bit counter. So what we have been proposing is to raise the level of abstraction and to use C software programming languages and building synthesizers that can then generate the hardware circuits automatically. And you see one of the advantages here. If you want to build an 8-bit counter, this is the code that you would write in Verilog and VHDL. If you write C code, it's only 1 line of code. So you be much more productive building these complicated hardware circuits, writing C, MATLAB, C++, rather than these low-level hardware description languages. And what are the benefits? What are we doing now? What are the challenges in the future work? Is what you see in this slide here. What we're doing is basically designing methodologies to allow people using these low-level hardware description languages to pull them into our world, to start using C-based high-level synthesis, and we're adding new design dimensions like low-power hardware security and fault tolerance to make it easier to design these complicated integrated circuits.
Thank you.